In this video, we're going to introduce the dot product. Now, the thing to remind yourself of from what we just studied about vectors is that we can add them, we can subtract them, we can also multiply them by a number, by a scalar, right? But we haven't talked about if there's any such thing as taking a product of two vectors. And in fact, there is, and there's actually more than one type of product of vectors. But for now, we're just going to stick to this one called the dot product. So here's how you define it. So if you have a vector or two different vectors here, then you define the dot product by saying that we are going to multiply the x components together and then add that to multiplying the y components together. So the first thing to notice is that when you take the dot product of a vector, it gives you just a number. So there's no more vector here. So the dot product is always equal to a number. So just to provide a concrete example, even though the definition's pretty straightforward here, here's how it works. If I want you to dot these two vectors, A and B, then what I'm going to ask you to do is just take that -5 times the 2, because those are the x components, and then add that to 3 times 6, since those are the y components, and then just simplify that. So what we have here is that the dot product of A and B, these two vectors, is the number 8. And of course we can apply this same idea when we're using the IJ notation instead. Same thing applies, so we still have our x and y components. So we get 4 times 3 is 12, and then 6 times 7, or 6 times -7. Kind of jumped again there, sorry. 4 times 3, and so then we get 12 plus -42, which is -30. So a dot product can of course be positive, it can be negative, and so that's how you do it. Now, both in this section and then as you move on in mathematics, you'll learn more and more about this dot product and how important it is and what exactly it tells you. But for now, just know that it's a product that takes two vectors and gives you a single number. All right, so what kind of properties does the dot product have, right? We know that multiplication of numbers has certain properties, like the distributive property or the associative property, things like that. So what kind of properties do we have here? So we have the commutative property, which says that the order doesn't matter when you take a dot product. It doesn't matter which vector's first, which one's second. This one says that you can use both the associative property and commutative property with scalars. So you can have a scalar times a vector, dot it with another vector, or you could pull that scalar out and multiply after you take the dot product of the two vectors, or you could multiply it by the second vector first and then do the dot product. None of that matters, okay? And then the distributive property also works with dot product. So if you have two vectors added and then you dot that result with another, then you could have just dotted the third vector with the first two and then added. And then finally, this one's going to be really important to us. Note that taking the dot product of a vector with itself is the same as squaring its magnitude, okay? And the reason for that is, if u equals xy, then we know that u dotted with itself is going to be x squared plus y squared. All right, but then we also know that the magnitude of u is the square root of x squared plus y squared. So if you, of course, square that, you get the same thing. So this is a real important interchange to be able to make. All right, and we'll actually make it down here when we prove this formula. All right, so this formula here, it's called, so the geometric definition of a dot product gives us an alternate way of computing a dot product, especially when we know the angle that goes between two vectors. All right, so what it's claiming here is that u dotted with v is the same as just taking the magnitude of u times the magnitude of v times the cosine of the angle. And I actually really like doing the little proof here because it's not too hard and it's familiar to you. So if I went ahead and connected another vector between these two, if I do this vector right here, this vector here is u minus v. But understand that what we've done is we've created a triangle here, right? And I know it kind of looks like maybe it's a right triangle, but even if it is, that's just by coincidence, so let's not assume that it is. But what I can do is I can use my knowledge of the law of cosines to prove that this is true. And so the way that that works is I'm going to set up the law of cosines, understanding that, understanding that the magnitude of this vector, and this vector are just the side lengths of this triangle. So the law of cosine says that the square of this length is equal to the square of the magnitude of u plus the square of the magnitude of v, because those are these sides of the triangle, minus 2 times the magnitude of u times the magnitude of v times the cosine of the angle between those sides. So that's all just the law of cosines that we already know. Now up here, number 4 in the properties tells us that this is the same as just u minus v dotted with itself. All right, and then we still have all this. But when we dot u minus v with itself, we can just essentially FOIL, right? I mean, it's u dotted with u would be the magnitude of u squared minus 2, minus 2u dotted with v plus the magnitude of v squared, right? And both of these I'm doing because I'm taking u dot u, which is the same, right, as the magnitude of u squared and the magnitude of v squared. So what we get is a bunch of the same stuff on both sides. Right? If I've got a magnitude of u squared on both sides, those can go away and those can go away. So I'm left with just this. And so if I then take and divide by negative 2 on both sides, then I'm left with u dotted with v equals magnitude of v cosine theta. So this is another way of computing our dot product. And it's also a way of getting information about our vectors. Okay, so in example 3, it asks us to find the angle between 4, -3 and 1, 2. And I think before we start, it'd probably be a good idea just to sketch a quick graph here and go ahead and just do an approximate sketch of these vectors. So here's my u, or my a, excuse me, and then my b is 1, 2. Okay, so I'm kind of thinking probably somewhere in the neighborhood of 90 degrees is what this angle ought to be. Maybe not exactly. So what we can do is say, all right, I can calculate a dotted with b, and know that's the magnitude of a, magnitude of b, cosine of theta. All right. So let's figure out what's the magnitude of a. Well, that's the square root of 4 squared plus negative 3 squared. But that's just the square root of 25, which is 5. And then the magnitude of b is the square root of 1 squared plus 2 squared, which is the square root of 5. So and then of course a dot b is going to be 4 times 1 plus negative 3 times 2. And that's going to equal 5 square root of 5 cosine of theta. So this simplifies to negative 2. And then of course I can get my cosine theta by itself. But then I know then that theta will be the cosine inverse of negative 2 over 5 roots of 5. And so I get about 100.3 degrees. And remember, we were predicting something around 90 degrees. I think this qualifies as being around 90. So we're saying that that's about 100.3 degrees. Now I did some algebra to get there by going with this original formula, but let's understand that we can just permanently solve for cosine of theta if we'd like. So here's another formula you could remember if you wanted, if you didn't want to always go back to this. So the cosine of theta is always the dot product divided by the product of the magnitudes. All right, now a couple of things as far as whether our dot product is positive or negative or 0 even that are important is if the dot product is 0, then what you have are orthogonal or perpendicular vectors. Okay, this word orthogonal just means perpendicular. The reason that occurs is because in this formula, let me just circle this one up here. In this formula, you're going to get 0 when the cosine is equal to 0. So when will cosine equal 0? Cosine equals 0 when theta is 90 degrees. So because theta being 90 would cause this to be 0, that's why we can say anytime the dot product is 0, our vectors are perpendicular. If the dot product is positive, then that means that your angle is less than 90, and that's because thetas between 0 and 90 always give you a positive cosine. And then, of course, it's negative when the angle is between, when the angle is greater than 90, like it was in this one. Okay, so notice that the dot product over on the left was negative 2. Okay, and that's because theta was 100.3 degrees. All right, so then, related to this idea of the angle between the vectors, there's also a concept we're going to introduce called finding the component of one vector along another. All right, and so what we already know is that if we have a vector, let me make a little sketch up here separate from the one we're looking at. Oops. Make a quick sketch over here. So we already know that, if I am looking at this vector here, and let's call this vector A, I already know that if it makes an angle with the x-axis, that the vector A is the magnitude of A times the cosine of theta, and the magnitude of A times the sine of theta. All right, so we already know that. This is the exact same idea. So what we're doing here is we're saying if I have these two vectors u and v, then if I take the magnitude of u times the cosine of theta, where theta is the angle between these vectors, then that tells me basically how big the shadow is, I guess. If there's like a light source up here, how big is the shadow that U casts onto V, okay? Or how much of U is going in the direction of V is another way to put it. And that's called the component of U along V. And you can think of this then as the component of A that goes along the x-axis, and this is the component of A that goes along the y-axis. So to kind of match the picture we're looking at, you could, color that in and color that in, I suppose. Okay, so basically we are doing this same idea that we've already done. It's just that now theta is the angle between vectors, and now we're going along this vector. All right, now with that idea in mind, we can relate this back to the dot product. So if you start off with the magnitude of U times the cosine of theta, if you multiply on top and bottom by the magnitude of V, then what happens is on top you've just produced the dot product formula. So that can become U dot V, and then on bottom you have the magnitude of V. So there's another way to figure out this idea of the component of one vector along another. So let's see how this works here. And I should have drawn some axes in here because I think it's really important to draw what we have going on here. So we're going to do that. Okay, so let's first just graph these. So we have 10, 4. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4. So we've got this vector here. So that's the vector C. And then we have the vector D, which is 3, negative 2. So that puts us right there. Okay, now what they're asking us to do is find the component of D along C. So to match that picture up there, the idea is let's drop this straight down to make a 90-degree angle with C, and they're asking us basically how long is this shadow that's cast. So that's what we're looking for. So you can already tell, we're probably trying to, get an answer that's around 2 or 3 or somewhere in there. It's not going to be really very big. So that's what we're searching for. All right. So the only thing that you got to remember is that when up here when it says the component of U along V, you're taking the dot product and then you're putting the magnitude of the vector you're going along on the bottom. So since we're doing the component of D along C, we know that the computation that we want to make is D dot C over the magnitude of C. Okay, because we're going along C. So you can think of it as the one that appears more in the formula is the one that you're going along. All right, so we've got 10I plus 4J. Oh, I guess that's my C. I'll write that second just to be more clear about it. So 3I minus 2J dotted with 10I plus 4J, and I'm dividing that by the magnitude of C. So that's the square root of 10 squared plus 4 squared. So we get 30 minus 8 over the square root of 100 plus 16, which is equal to 22 divided by the square root of 116. And I could do a little simplifying down there, and I guess maybe just to, it's a good exercise. You can turn 116 into 4 times 29, which allows you to take a 2 out. So then that allows you to cancel a little bit. So 11 over square root of 29. But let's, put this in our calculator and check it, right? Because I want to know, is it matching up with this? Well, that's pretty close to 2. So it seems like that's just about right based on our picture. So the length of this shadow essentially that that's cast by D onto C is, about a length of 2. All right, so the last thing that we're going to do with the dot product is we're going to see how it applies to physics. So don't worry if you haven't taken a physics class, we're going to keep this real simple. But what we're going to look at is the concept of work. Now, work is a measure of how much energy is involved in a process. And so the way we define work is to say that work is force times distance. So to understand that, probably one of anybody's least favorite things to do for a friend, but it's something you got to do if you're a friend, is to help someone else move, right? And the reason that's no fun is because what are you doing? You're doing lots of lifting, and then you've got to carry those things that you've lifted, typically pretty long distances, right, back and forth between the truck and the house. So the idea here is that the reason something like moving is so much work is because you have to exert a lot of force, but you also have to do it over large distances, okay? So that's kind of a way to understand why force times distance makes sense. And so if I ask you a question like, find the work done by a person pushing 90 pounds of force on the back of a car if the car moved 40 feet. Okay, so you're pushing a car that's died. Take the 90 pounds, that's my force, times my 40 feet. And that's going to give me 3,600, and the unit here is pound-feet or foot-pounds. Okay, and that's the work done. Okay, now there's no dot product there. Okay, but here's where the dot product comes in. Is in the case that I just gave, where I'm pushing on the back of a car and moving it 40 feet, all of my force is going in the same direction as the movement. But oftentimes that's not the case. A lot of times we're applying the force in a different direction. So a good example is like, pushing on a lawnmower, right? When you push on a lawnmower, because of the angle of the handle, you're pushing forward some, but you're also kind of pushing down. So not all of your force is helping you toward moving the distance that you're covering. So what we want to do is take this idea of work equals force times distance and understand that really you should only be keeping track of the component of the force that's going in the same direction as your distance. So the component of F along D. Okay, so if we do that and multiply that by the distance, then that makes sense. But we just learned on the previous page that the component of F along D is the magnitude of F times the cosine of theta. Okay, I'm just going back to, on this previous page, this definition right here. Okay, so when you do that though, then you can rearrange and notice that it's just F, the magnitude of F times magnitude of D times the cosine of theta, but guess what? That is the definition of the dot product. Okay, so when we are asked these work problems, what we want to do is understand that work is going to be the force vector dotted with the distance vector. All right, so in example 6, it says a child pulls a wagon along a level ground by exerting a force of 20 pounds on a handle that makes an angle of 35 degrees with the horizontal. Find the work done in pulling the wagon 100 feet. Right, so we've got our wagon here, but the handle, right, is coming up like this, right? Making 35-degree angle. So what we have is the child's force is here, but the direction vector here is in this direction. Okay, so not all of the child's force is going toward pulling the wagon forward. So what we can do is we can say, okay, my work is my force dotted with my distance. which I also know is the magnitude of my force times the magnitude of my distance times the cosine of the angle between them. Well, the angle between them is 35 degrees, right? And so now I can just put these in, right? 20 for the 20 pounds of force, 100 for 100 feet, and then I get 1,638.3 pound. So let's do one more example here. So in this one it says a small cart that is weighing 100 pounds is pushed up an incline that makes an angle of 30 degrees at the horizontal. So here's our incline here. So we're making this 30-degree angle here. Okay, and so we've got this cart that's right there. Now it says find the work done against gravity. Okay, so that means that if we're working against gravity, gravity points down, right, toward the ground. So that means going against gravity means the force that we're interested in is going up. And then our D would just be, well, the cart's clearly moving up the incline like this, so there's our D. Okay, so to talk about the work done against gravity, all we need to do is say, well, okay, what's the magnitude of my force? What's the magnitude of this direction vector here, and then times the cosine of the angle between them. Okay, but what is the angle between them? Well, here's the deal. We know that this is 30, right? Right, because the incline is 30. So that must mean that this is 60 degrees. And so I put 60 degrees in here. Well, I guess I'm going to put theta in there because I'm just using the symbols. But then here I'll put the cosine of 60 degrees, 100 for F, and then 80 for D, or for the magnitude of D. And so what we get there is 4,000 pound-feet. Now I do want to do this one in another way. You might be wondering, okay, well, we've done this as a dot product. Could I do this by, multiplying the x's and then adding the y's multiplied? And the answer is yes. So if you wanted to, what you could have done is this. You could have said, well, let's take my F vector and let's put it in component form. Since we're talking about the force against gravity, there is no side-to-side force there, so we put 0 for the x, and then we put 100 for the y. And then remember, if you want to write out the components of D, you need to take the magnitude of D, which is 80, times the cosine of the angle. But what are we talking about there? We're talking about the true angle that D makes with the positive x-axis. So that would be this 30 right here, right? So we would say 80 cosine of 30, 80 sine of 30. So if you wanted to, you could do the dot product using the first definition of the dot product that we introduced. And at first, when you're doing this, after doing it the first way, you might be kind of nervous because you're looking at this saying, this doesn't look the same. Well, no, it's not the same. But of course, what you're going to do is you're going to multiply the x components and get 0, right? So the only thing that survives is the y components multiplied. And the reason all this turns out okay is that the sine of 30 degrees is actually the same as the cosine of 60 degrees. So we end up with the same exact thing, 4,000 pound-feet. So this just goes to show you, you can use either one of our dot product definitions and arrive at the exact same answer.